Alrighty. So you guys doing well? It's Friday. You good? Okay, perfect. So let's start the what we left on Wednesday. So we talked about the stereoisomers. One of them was about enantiomer, or what you call enantiomer. So if you have anything that on carbon, there's four other groups, maybe like this. This should be. You should be able to draw some mirror image, but that is not the same. Okay? So maybe you can do this, 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 okay? So even though you do try to put it on the same plane, there will not be same compounds anymore, even though it's mirror image to each other. So that means you have a chiral center over here, the carbon that has four different groups on that carbon. Okay, and so that was last part on Wednesday. So maybe we can try to do some practical problems. So we draw one compound. So this is menthol. Do you guys like chewing gums? Peppermint, like maybe? Good. So this is a common compound in the peppermint plant. It also gives a lot of the flavor and smell about like a mint. So this is maybe one of the common compounds you can try. So maybe if you look at this one, maybe you can try to find the chiral center, or you can say chirally center. So what you can do is quite simple. You can try to go on each carbons here, 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 here. So there's so many carbons, but like I said, if that carbon has four different groups on that carbon, we can point that as a chiral center. So if you look at this one, those two are not good because they are bound to three other hydrogens, right? So it's not. How about this one? You have a set carbon here, but this also has a two methyl group which are same. So this is maybe not. This one, this carbon has this group, right? And this group. And also this group right here. Okay? And then what you don't see is hidden hydrogen. So it's going right here. Okay? So think about it. There's a hydrogen, one group, R group here, right? A Q group here. And there's a one on half of this ring structure, the other one. They're not symmetrical here. So we can consider these two as different groups because it's not symmetrical, okay, because of this one. So then it has four different groups: hydrogen, RQ group, not asymmetrical on this ring on both sides, right? So before, so this is one of the chiral, okay? And then those two, if you look at this one, you also don't see hidden two hydrogens. So those you see now have two hydrogens on those two. So those are not chiral center either. Okay? So but this is, and also hydroxyl group, hydrogen. We go symmetrical on this side, they're different. So this is also chiral center. This one, hydrogen, methyl group, is symmetrical on both sides still, also different, they're asymmetrical, right? So they also four different. It's also chiral center. So let me rewrite this one. In here, in methyl group, there are three chiral center, which is here, here, here. Okay. So the tricky part, the most tricky part for finding a chiral center is finding a hidden hydrogen. So we don't normally show you the hydrogen on here, skeleton structure. But you can always assume there's hydrogen here, because this carbon should have a 4 bonding structure for sure. So 1, 2, 3. There gotta be one with the hydrogen, but it's just shown in the structure. So same here. 2, 2, 2, 2. And whenever it's on the ring structure, so it actually it doesn't look like a separated. In that case, those two groups can be distinguished by symmetrical or asymmetrical on both sides of the ring. So if it's not, it's still considered two different groups. If it's same, it's much the same. So it's not kind of same, but it is different. So there, and yeah. So there's a 2 hydrogen here too. Okay. So just so this is the tricky part. So maybe you need to kind of consider. Oh, maybe hydrogen is not there. You can try to see how many hydrogens should be there on carbon based on how many bonds are made in the skeleton structure there. And see how many chiral centers you could possibly find in their compounds. Okay? Does it make sense? So just try to find the carbon that has 4 different bondings, groups.
Where's the hidden hydrogen?
Oh, so hidden hydrogen means, so in this structure here, we only show the bondings between carbons, right? Okay, carbon and carbon. But the carbon is group number 4. So that means carbon has 4 valence electrons. But for each single bond, you only need to contribute 1 electron. And there's another one comes, so pair of electron will make a single bond, right? That means this carbon has the 2 electrons left over here. So that means we don't show you here, but it's actually making bond to hydrogens like this. So that's actually a very good question. That is why if there is maybe not just 1 but 2 methyl groups, maybe on here, for example, there shouldn't be any hydrogen here, right? Because this is a carbon. There's 2 methyl group, carbon, 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 carbon. So it's already 4. Then there's no hidden hydrogen. It's just there's no hydrogen, literally. Maybe this will be 1 hydrogen. If there's nothing, maybe 2, and so forth. That's a very good question. So try to make sure that carbon can have at max 4 single bond. But if you don't see 4, assume there's hydrogen. Okay. If there's 4, you don't have to, because it's starting to do with carbon. Okay. Good. That's a very good question. So this is one tricky part, but you can maybe go more practice. Also, we can do it in a review session in next week. Okay. So just one more thing before we actually getting into some conformations and the stereoisomers. One thing what we need to do is that those compounds that are optically active. Okay. So optically active means those compounds that actually affects on the light. That's why we put it like optically active. So what I mean by that is, do you guys recall what you have learned in the Gen Chem 1 and 2? So the light is electromagnetic radiations. Okay? So it's kind of a I can say funny object. As a scientist, it does quite weird things to in our nature, a lot of aspects here. So what it really means is light actually informable energy. So they can create it by emitting a certain form of energy through the space. So if this is the direction of the light, they're going to show you transverse wave. That means they're going to show some oscillation on the perpendicular to the direction of the wind is heading. So this is one wave, which is electrical field oscillating. And to this plane now, once the perpendicular to this electrical plane field, you have a magnetic field as well too. So this is sort of a self-propagating radiation. They actually oscillating these two different fields perpendicularly, even to the way they're heading in the space, and it sort of makes the light. Okay? So, do you guys remember the light is kind of weird thing? It has dual nature. It sometimes kind of behave like a particle, but it's not really particle actually. It is at least so far. But most likely they do also a lot of wave. So you consider this. There's like a small quantum of light, like a photons, kind of behave like a particle, but also like a wave, oscillating these two different fields perpendicularly, even also to the direction of the heading, this directions. Okay, so this is all you have to know. So now we know for sure in light there will be a lot of oscillating in the fields. Okay, so maybe we can polarize. Maybe you can polarize light. Okay, using we named it also a polarizer because it will polarize the light. So like I mentioned, in a light, there's a lot of source of energy for sure. That means those can actually oscillate in a plane, but in many other different planes as well. So they can go in like this degree, this rotation, this way. So many other different planes they can oscillate it like through when they kind of go through the space. Okay, so if that is true. Maybe you can shoot the light. Okay, maybe there's some light source here, light source. Okay, and then shoot the light, and we're gonna make some polarizer. Usually they're made in synthetic polymer like plastic or the natural crystal, which they will give you a very uniform arrangement of the atom that makes quite a nice arrangement on where they can light can go through along with the electrons. Anyway, so whenever that has happened, now we had a lot of different planes oscillating in the directions. But in the goes now, the one that is again past this polarizer goes passing this way, up and down, or you can say it's 180 degree up and down in this. And then you're actually going to put it through the sample, your sample. Any compounds, you're going to put it in that tube, okay, sample tube. And then if that does, when this polarizes the light, go through the sample. And then when it comes out from there, it may be rotate a certain degree. Okay, then you're going to detach by analyzer. Okay, analyzer. So you can see, oh, this polarized light has been rotated slightly. Okay, then if you, so this is quite important. This is your eye. So you're actually looking at it from like what comes from like through it. Okay, I'll tell you why it's important later. So you're actually looking at it through that light coming into you. Okay, does it make sense? So then, if that in that way, if your light maybe rotate in the clockwise, okay, we call this dextro rotatory. Okay, if it maybe this polarizer goes this way to the left, maybe you can say counterclockwise, maybe you can go this way, right? Okay. Then we're gonna call this levo rotatory. Okay. So, and also when it's the dextro rotatory, it's we put the positive symbol there. If it's a levo rotatory, we put negative here. So whatever the compounds that gives the either right or left, you give plus and minus sign, the indicating that would be either dextro rotatory, optically active, or levo rotatory, either way. Okay. So this is only this is how we can define those optically active compounds when it should be a polarized light and see how is it rotating over the tourism. So obviously, when you look at this one, when the light will be more rotated when it hits more numbers of what? Compounds, right? Obviously, right? So we actually made some standard conditions for it. So that is the one that matters for the rotated angle. It would be numbers of compounds. Okay, that means whenever you make this one longer, there will be more rotation, right? Because they'll hit more compounds. Or if it's the same length, but if you make it higher concentrations, high concentration simply means there will be more numbers of compounds in the same space, right? So this rotation will be affected by the numbers of compounds, meaning path length. We call this path length. It's the length of path. So just if it's longer, it will be more rotated. If it's highly concentrated, it will be also more rotated because there's so many more kind of compact in the small same space there. So the scientists try to make maybe we can make one standard conditions for this one. We call this specific rotation. And the symbol for this one is the alpha in bracket with D. So let me. So this D is from our like sort of a reference light source. We use the same source, which is the sodium metal vapor kind of D line light, because it has about 586.9.6 nanometer wavelengths, and there's a temperature, but we're gonna ignore it today. Okay, so just to stick to this one, and then this is going to be governed by. This is just alpha, just any angle you see on the analyzer. So we can call this observed rotation. So whatever you see in that experiment, okay? But they will be governed by what? The path length. Right? We're gonna use decimeter. So 1 decimeter is equal to 10 centimeter. And then also this will be also governed by concentration. We're gonna use gram per centimeter cube, or you can say gram per mil. It's the same thing, right? Gram per mil or gram per milliliter or gram per centimeter cube is the same thing. Okay. So, oh wow, what does that really mean? Okay, let's try to do an actual problem here. So this is a fixed value. This will never change because this is governed by 1 decimeter and 1 gram per centimeter, and this wavelength. So whatever you see in here will be different, but this number for the same compound will be always fixed because this is the one that measured by same conditions. So whenever you have this one, you apply the other the number for the path length and the concentration for that experiment, you still get the same number over here. Okay? All right, so let's try to do some practical problems here. Okay, so we have corneum. This is compound. It's like toxic plane in the toxic plane. So, okay, this is what it looks like. And say, let's say we have the observed angle. So it was maybe tilted in the right way, so it's plus then. If you tilted the clockwise, it is plus, right? And maybe it was 1.21 degree. It rotated in this much, which is your R part, right? But obviously, we didn't follow the standard condition 1 decimeter or 1 gram per centimeter. So let's say we use the 5 centimeter path length, which is equal to 0.5 decimeter. Okay, and let's say concentration was about maybe 1.5 grams in 10 mL of ethanol. Okay, so that makes your concentration equal to what? 0.15 gram per ml, or you can say centimeter cube, same. Okay, so now we have everything here. Okay, so now we can try to do is you just need to get all the numbers for concentration and path lengths in the right unit, which is decimeter and gram per centimeter cube or gram per mil. And then plug those numbers on here in this equation here. So now it's not 1 anymore, right? So we're gonna change this one to 0.5 decimeter. Okay. And now this is going to be what was it? Oh, yeah, 0.15 gram per mil. Okay. And then obviously this is this one same, right? Plus 1.21. Okay. So that's it. That's done. It's just a couple, several calculation work. It makes your number for specific rotation for your conium. So there will be here 1.2 divided by multiplication of these two. So there will be approximately plus 60.1. Okay, so that's it. Okay, so this is pretty much everything. So if it's plus, now you can say this is going to be dexa through rotary or dexa, right? Dexa. So it means whenever light goes through this sample, it will rotate on the right, in the clockwise. Perfect. So maybe the good example for the opposite of this one would be cocaine. That actually has specific rotation of cocaine is about -16. Okay, -16. So maybe I can give you an example problem like this, but in the other way, like I did over here. So maybe you can say this, if that is the right, and then maybe I'll give you, so we find that when we made the cocaine in here, concentration was maybe 0.5 gram per mil or centimeter cube. And we also used 0.5 decimeter, which is 5 centimeters. And what might be the observed angle there, right? So you just need to do the other way. So just what you need to do, right? This is x divided by 0.5 and 0.5, right? So you just need to go here. So your x will be what? 4. Okay? -4. Okay? So it would be negative. That's the levorotatory compound. That is the cocaine. It makes sense, right? It's just you just need to know which one goes which in the equations and plug all the numbers in. And either you can look for the given number for your specific rotation or the observed rotation, and you solve for the other one. Yeah.
So that'd be -4 degrees.
Yeah, degrees. Yes, perfect. That's a good question. That's actually a good question. Yeah, it's 4 degrees. But sometimes people, not really care about the units. But yes, All right, so if it all makes sense, can I move on? Okay, good. I'll move on. You guys did really well. If you understood it at once, that's very good. So obviously, there's other things before we look into the other type of stereoisomers besides the enantiomer or mirror image or optical isomers. One thing what you need to do, oh, time. It's Friday thing, time goes really fast. Anyway, so no? Okay. This is what we call Kahn Ingold preload convention. Okay, so now you guys know, oh, what does that mean? Kahn Ingold impairment. It's just the series of the last names of three very famous organic chemists. They're all famous people, and we just name after those three awesome great organic chemists. So we call this Kahn Ingold preload. This is their last name convention. So what it really means is you're gonna actually find out the configuration of the optical isomers by giving some priority on each group of the carbons. So for example, there's a lot of steps you can follow in the textbook, but if you can watch me and listen to me carefully, actually you can get this in quite a much faster pace. So there's a very famous let me draw. Sorry, I drew this again. So this is very famous example for this type of questions. Is the 2-butanol, right? So once again, what you need to do, maybe I can put it in this direction. So maybe you can do this, okay? And then there's 4 carbons, it's butane, but it has functional group is hydroxyl, so it'll be alcohol, butanol, but 2, so it'll be 2-butanol, okay? And tell me, please, do you think this is chirocenter or not? So you have a methyl group here, ethyl group here. I mean, not as group, but from here, right? 2 carbon chain, 1 carbon chain, and 1 hydroxyl group on the here. So is it chirocenter, chirotic center? Yes, perfect, because there are hydrogen hidden here. The 4. Okay, makes sense, right? So carbon should have always 4. Like I kind of make sure there's always might be hidden hydrogen. So it'd be 1 hydroxyl group, 1 carbon, 2 carbon chain. All right. So they are different too. They are different too, and hydrogen obviously different from others as well. Okay. So this is for sure our chirocenter. If that is the case, what we can do is you can actually prioritize by the neighboring atom, its atomic number. So what I mean by that is, if you look at the periodic table right there, right? The oxygen is higher in atomic number. Do you see that, right? You see that, right? Over there, right? Okay. So that means this is prior to carbons. So if you look at this one here, this carbon has, maybe I'll draw bigger, sorry. Okay. So if you look at this carbon here, it has carbon over here. So this one, like this. So this is the number 1 because it's highest in atomic number. If you look at the periodic table, right? And those 2 are second, and this is 4th. Okay. And now you wonder, okay, now you have 2 carbons, right, on this carbon. So they are in the same in atomic number. What should I do? Then what you need to do is from these 2. So this is the least. This is the highest, right? Obviously, because hydrogen is always the lowest. Well, also lowest in atomic number. But this one, what you can do is try to go even further from there. So if you go further from this carbon now, it will be 3 hydrogen, right? 3 hydrogens. So we can say hydrogen, hydrogen, hydrogen. Okay. But if you look at the one over here, it has 1 and 2 hydrogen. The other one is pointing on to what? Carbon, right? So it'll be carbon, hydrogen, hydrogen. Okay. So as you can see, among these two same carbon, because of the neighboring atoms, which is 3 hydrogen here, 1 carbon, 2 hydrogen, this is higher than this carbon in priority. Okay. So now we know then is going to be 2. This is going to be 3rd. Okay. And this is 4th. Okay. So now when you're done, what you need to do is look at where your hydrogen is, and then try to put that hydrogen or number 4, the least priority, the groups on the back, and you're looking at those 3 bondings to your face, but holding your 4th group on the other position. So hydrogen is heading now this way. Okay, hydrogen is heading now from my eyesight. I'm looking at this right now. I'm holding it. Now you need to know it's tetrahedral structure. So I'm holding hydrogen 4, going opposite direction and this way, and those 2 should be over here, like almost triangular planar to me. But you're holding the other one on the other side. That's why it looks like a planar straight. But that means it's already going backward from this blackboard here. So you actually need to just find the connectors number 1, 2, 3. Okay. That's it. So if you're holding it like this, it goes 1, 2, 3, goes, okay? Like a 1, 2, 3. Just count the number there. So if that is going clockwise, we're gonna call this R configuration. So if it's going counterclockwise, we're gonna call this S configuration as your center. So I think the best way to memorize this one would be this one. I don't know how you write your R. I usually write R like this, right? Then you actually writing this way. Yeah, go ahead.
So are you only using the atoms that are around the center carbon?
Yes, yes. From here. So this is the one we are kind of trying to figure out if it's that is kind of center, right? Then this carbon from here, just first you only go to 1 step, like a 1 further neighboring atom first. But like here, you still have the same atomic number element there. Then you go further from there. If you already have a nicely prioritized and just 1 step away from your central chiral center, you don't have to. But in case you have the same elements on your neighboring, your chiral center neighboring elements, you can even go even further from there. Then you find the slightly prioritized even in second order. That's why I gonna prioritize in 2 and 3, not 2 and 3, because the 3 hydrogen is less than 1 carbon, 2 hydrogen.
Okay, got it.
This is kind of some practice required, but you'll see it once you get this. But did you get that like a thing? Okay.
Yeah.
So that means right. So let's try to do it the other way. Okay. I'll do just a little more and I'll finish it. But so maybe you can try to do it this way. So maybe we had the same. How about we now putting like this? Okay. Now we had to put it in this one, this way. Okay. And then it's the same, right? This will be 1, 2, and 3 and 4 as we did it, right? Okay. Okay. All right. And then what you need to do is if you're putting it. Okay. So this is now not going back, going forward, right? So if you're actually getting this one, and you go there. So does it make sense? The before one was already going backward, right? So holding it like that, it was just there already. But if now number 4, you need to grab it toward your face. It's going now this way, right? Then this hydroxy group going backward, like here, here, here. So if people actually go this way, the 2 goes this way. Because you now facing it from the other side, not here, right? You're looking at it from here, goes this direction, but if you're going from here, it's actually going the other way. Because you're looking at it opposite directions. Because now it's sticking forward. So you try to put it in the back again, that will be actually going this way. So this is now S now. Okay. This is obviously, I think, kind of. Let's try one more example. I'll show you one more example. Let's do one more, okay? I know this is this not. It's the same thing. I'll just make one. I'm sorry. There's not much good. So maybe I'll make one. Okay. So maybe if you have same thing here, but okay. Okay. So maybe you can tell me if this is the kite center or not first. Yes, perfect. Good. 1, 2, 3. They are different too, and also we have hydrogen hidden here, right? Okay. So let's say we have this one over here. Okay. And then this is also even a bit more trickier than before. Now you have all carbons on except the hydrogen. Okay. So, but still, we're gonna stick to the same rule. So, this one now has carbon, oxygen, oxygen. This carbon has 3 hydrogen. This is carbon, carbon, hydrogen, hydrogen. So, let me write this one: hydrogen, hydrogen, hydrogen. This is carbon, hydrogen, hydrogen. So, carbon, hydrogen, hydrogen. This is actually a pretty good example here because for here, if you see the double bond here, right, that means you counted 2. So it's not just O, O, but it's O, O from here, and O. 3 O's, not 2. Because of the double bond. Okay, so now we know, oh, maybe we know those oxygens are higher in atomic number and mass for sure. So maybe this one is very higher prior to those 2, so this might be the first one. And these 2, also this is a bit higher than this one, so it will be 2 and 3. Okay, so this is another example you can try when it has double bond with its neighboring elements like oxygen and nitrogen and so forth. Okay, so in this case, it's quite easy now because now your hydrogen is heading back, right? So you just hold it like this. You're looking at it just the way it is. So it would be R or S.
R.
Perfect. Perfect. That's good. So if I change this one to this way, you have to looking in the other direction, right? That would be S. Perfect. There you go. You guys did really awesome today, I think. Oh, and I'll tell you whenever you're hydrogen groups on the plane, it's kind of hard to tell. And I'll try to tell you how to do it. It's a bit more slightly complicated. So I'll do this on Monday, and also I'll try to finish up the last part of chapter 5 on Monday, and so we can do review on Wednesday and Friday. Okay. All right. Thank you guys. This is pretty okay, right? So far, we good? Okay. Thank you guys. You guys did really well.